Lesson 70 is properties of limits and some special limits. So we had properties of integrals not too long ago. Okay, what you are and aren't allowed to do with integrals. This is what you are and aren't allowed to do with limits. So the first 7 things here are just some explanations. Okay, some of these are pretty, I don't know, is obvious the right word? You know, it just seems really logical. Some of them are a little bit different, things that you haven't necessarily heard. So, with that in mind, 1, the limit of the sum of 2 functions equals the sum of the limits of the individual functions. What that's saying is if you have the limit of f plus g, that is the same as doing the limit of f plus the limit of g. Okay, so it just changes whether you add the functions and then do the limit, or whether you do the limit of each function and then add those responses. Okay, so it's just showing up, and it shows up there that the addition can be broken into 2 limits. Number 2, ditto that, but with subtraction. The limit of the difference of 2 functions equals the difference of the limits of the individual functions. Okay, so same thing. The limit of f minus g is the same thing as the limit of f minus the limit of g. Number 3, ditto it, but with multiplication. The limit of the product of 2 functions equals the product of the limit of the 2 functions. So the limit of the product, so the limit of f times g, is equal to the product of the limit. So limit of f times limit of g. Okay. 4. Reminds me of the integral in that if you have a constant, you can pull that out in front of a limit. So like if you have a constant number in an integral, you can pull it out front before you integrate, or before you plug numbers in. Same thing here. The limit of the product of a constant and a function equals the product of the constant and the limit of the function. So you can leave the constant in with the function, which is sometimes fine. Or if it's making life more difficult, pull the constant out front. Number 5, the limit of the quotient of 2 functions equals the quotient of the limits of the individual functions, given that the limit of the denominator does not equal 0. So again, same thing, but with division. So those are the ones that, to me, they seem pretty obvious. They seem, just kind of assumed. Okay, number 6 is something we're going to talk about called the sandwich theorem, okay, referred to as the sandwich theorem. And when it comes to, and I know we haven't practiced this really yet because we haven't even really looked at any open-ended free response questions, but being able to justify something and say because of this theorem or because of this is something that you'll need to be able to do on AP. So as we look at number 6, if the value of a function g is greater than or equal to the value of a second function f, and less than or equal to the value of a third function h, and if f and h both approach the same limit L as x approaches c, then g also approaches L as x approaches c. Got it? Okay, so as I said, it's called the sandwich theorem. So,
approach the same c value.
If the outside 2 equal L, then the middle one has to equal L also. Right. Okay, so right here, first of all, it's saying that f of x is less than g of x is less than h of x. I am. I can. That's helpful, isn't it? Okay. Sorry. Okay, so f is less than g is less than h. That's just saying the value of the function. F is smaller than g, g is smaller than h. So basically that's saying that g has a value that is in between f and h. It's bigger than f, smaller than h, right? Now, they're saying if these 2 outside limits equal each other. It's getting bad. He's throwing pencils here. Okay, so if the 2, so the smallest one, which is f, and the largest one, which is h, if they obviously have to approach the same thing, so the limit as x approaches c, if both of those limits equal the same thing, L, so your smallest function equals L and your largest function equals L, then by the sandwich theorem, that means your middle function has to equal L as well. Okay? I forget, do we have a picture of this later? We do have a picture of it later. Okay? We do have a picture of it later, which is what I want to make sure of, but, excuse me. The idea is, if I draw a picture, I'm going to draw the same picture we're going to have later. So if that is, if I just draw that parabola, this is f, and then I draw this cubic, or I'll make it a sine function. Why not? You know, if this is h of x, and so this point right here is c. Okay, and then this point over here is L. The idea is, as f approaches c, so as x approaches c on the f function, what y value is it approaching? L. H. I just realized I should have flip-flopped these. Oh well. As x approaches c on the h curve, at c, what is my y value? L. What this is saying is, we don't know anything about g, but g will have to have the same limit, because g goes in between. Okay? Because g is in between. Now, technically, I should have put s down here and h up here, because f was supposed to be smaller than h, but that's the visual of the sandwich there. Okay? And that's a good one to recognize. So, we'll talk about it here in a moment, but does that picture help some? Okay? And we could, maybe it'll help later, because instead of C and L, we'll have numbers later. Okay, one last one before we move on to actual examples. Number 7. If the limit as x approaches a of g of x equals L.
Wait, which one are you on?
Number 7. If the limit as x approaches a of g of x equals L, and the limit as x approaches L of f of x equals f of L, then the limit as x approaches a of f of g of x is going to be f of the limit of g equals L. It is a lot. We use that one later too, don't we? Yeah, we do. The idea is when this is going to happen, or when we're going to use this, is when you have some weird function or graph and you don't know what it is, but it's a function within a function. The idea is if it's a function within a function, you can pull them apart and just look at the inside function and find that limit, and then do the limit of the outside function. Okay? So, again, I'll show an example in the back, and it'll make a little bit more sense to you. Or I'll try and make it make more sense then, okay? If you'll give me a time, and we'll get to it. Okay, so let's look at example 1. Put some of these to use. Example 1. Let the limit as x approaches 2 of f of x equals 3, and the limit as x approaches 2 of g of x equals 9. Find the limit as x approaches 2 of 2 f of x plus pi g of x. Do you see how we're going to do this? Basically, you're going to be using a combination of what? 1, 3, 4, or even just 1 and 4 maybe. Okay. The idea that I can, excuse me, first of all, because this is the addition, you can officially separate it into 2 limits. Okay? The first limit is going to be the limit as x approaches 2 of 2 f of x. This 2 is a constant, though, so it can be moved out front. So I can write this as 2 times the limit as x approaches 2 of f of x plus, and I can do a similar thing on the second one. It's the limit as x approaches 2 of pi g of x. Pi, again, is a constant, so you can move the pi out front, times the limit as x approaches 2 of g of x. That's what all my rules from above say is make this legal. Well, it's a good word to use, right? Legal. It's legal. Okay. So what do we do at this point then?
First one was 3 times 2, and the second one 5 times.
Yeah. You were given some information, right? The limit as x approaches 2 of f of x was 3. The limit as x approaches 2 of g of x is 9. We have those constants there. So 2 times 3 plus pi times 9. What is 2 times 3 plus pi times 9? 6 plus 9 pi. Look, more the noise coming from Mr. Stanley's room, and keep on moving. Questions on 1? Part of me wants to say that's obvious. I don't know if you guys see it as obvious or not, but it's pretty logical.
Just access variables.
Can we keep it as 6 plus 9 pi, or can we simplify it to 34?
Oh yeah, do you want it in terms of pi?
I would say leave it in terms of pi unless they ask for like a rounded decimal answer or something. Because this, notice I just did this problem without touching my calculator, right? And so that means this type of problem could make a good multiple choice, non-calculator. As opposed to if they ask what it is, you know, as a decimal, then they have to give you a calculator. So, okay, example 2. If the limit as x approaches a of f of x equals L, can we say that f of a exists?
Is this like a word problem, or are we still going to solve this with numbers?
We're going to reason it out with a picture, because I think a picture will help it make sense. Okay, so I'm going to draw, my curve here is going to be f of x. I'm going to draw how I want to draw this. Yeah, I'll just do it like this for the moment. I can always use the white out later if I change my mind. Okay, I just drew a random curve, yes? And this curve is f of x. As x approaches a. So that means a is an x value, yes? So kind of like the one I did up on the board earlier, where c was my x value. So a is some x value. So I'm picking that a is in that area. Okay? If the limit as x approaches a, so as we trace on this curve, and we get it equal to a, and it says equals L. So equals L means L is the y value. Because x approaches is the x value, what the limit equals is your y value. So right here, this is what it says. Can we say that f of a exists? So can we say that there is a point at that spot on the graph f of x? And I feel like this actually ties back to a multiple choice one you had on AP practice not too long ago.
Like the most recent one?
No. It was a previous one. Because it was one, it might have even been the first one, it was one that several people missed. I was kind of, let me change it this way. I'm going to, a 0 or a hole.
Oh, okay. It was a circle.
Okay, a circle, yeah. Okay, so now, have I changed the limit any? On this graph, as x approaches a, what is it getting closer to? The y value of L, yes? And that limit is still true because does this point have to exist to make this limit true? No, you can have a hole there. Okay. So can we 100%, are we guaranteed, do we know for sure that f of a exists? No, because like the example I just drew here, I made it that there's a hole there. Okay. So just because this limit exists does not even mean that f of a is equal to L. And according to the picture I have right now, f of a, we don't know what f of a isn't equal to anything because the graph does not exist at that one little point. So that means f of a does not exist necessarily. Yeah, I'm going to put an explanation down, but yeah, it's, we can't guarantee that because we cannot guarantee that that is a continuous graph without any holes. So, I'm going to say no. That's, the short of it. You guys can write your explanation as you want. I'm going to say as x approaches a, the value of f of x approaches L. We've already, that's what the limit says, right? So as x approaches a, the value of f of x, approaches L. However, that does not guarantee that f of a equals L, or that f of a even exists. Which word?
Guarantee.
I don't have problems with that word, but I do. I understand. I have certain words that I struggle with spelling, no matter how many. I just remember the one you guys struggled with on the multiple choice practice that you did at one point. If you recall, there was a removed point. Do you remember that?
Oh, the one that was all by itself?
Yeah, there was a removed point, so it'd be like that there's a point up here, maybe. Okay, so there's a removed point, and I don't know, you guys didn't pick it as the right choice, but here, the limit exists in that the limit as x approaches a equals L. However, that does not mean when f of a is equal L if there's a removed value somewhere. So that would mean that f of a would equal whatever this point is. So say that point is k. Okay? Does that make sense or not? Okay. Flip to the back when you're ready. We have another one to reason it out. Is the following statement true? Why or why not? If the limit as x approaches 3 of f of x equals L, then f of 3 equals L. If the limit as x approaches 3 equals L, then does f at 3 have to equal L? Right? Based on, so this is similar to the problem we just talked about, or the reasoning we just talked about in the last problem. Your limit can be approaching L, but does that mean that a point exists there where it equals L? No, that can be a removed point. It can just be an empty point and there's not anything that equals 3 there. Okay? So I'm going to say, is the following statement true? False. I'm going to write a similar explanation last time. Let's see. F of x approaches L as x approaches 3, but the function does not have to equal L when x equals 3. So I'm just putting it into words. Okay, I just wrote what I had just said. But f of x approaches L as x approaches 3, but the function does not have to equal L when x equals 3. Okay, example 4. If a function f is such that negative x squared less than or equal to f of x less than or equal to x squared for all values of x, what is the limit as x approaches 0 of f of x? Draw a picture. And Carly's saying, yeah, I have no idea what I'm supposed to be trying to visualize here. Draw a picture.
Two parabolas. And then that center point.
Okay, so there's my parabola. What we know about the function f of x is it's between negative x squared and positive x squared. What does negative x squared look like? An upside down parabola, and it goes through the point 0, 0. What does positive x squared look like? Okay, regular parabola, also going through 0, 0. So are you okay with that picture? Now, what do we know about f? Yeah. So we don't necessarily know what f looks like. Who knows what shape it is, but the idea is f somehow has to go between those two. I'm not saying it has to go between those two like that. You know, maybe the left and right look different. But what's the key here? They're asking us, what was the question? The limit as x approaches 0 of f of x. That's their question for us. So as you follow my purple dotted line, as x approaches 0, what's my y value have to be? 0. Because if both my above and below graphs go through 0, 0, what's the graph in between them have to go through? 0, 0. So the limit as x approaches 0 of f of x equals 0. Okay. If you want some backup, well, first of all, the limit as x approached 0 for x squared, what was that limit? As x approached 0 on x squared, that limit was also 0. And the limit as x approached 0 on negative x squared. What's the limit as x approaches 0 on negative x squared? As x approaches 0, it's also going to equal 0. What theorem is this? Yeah, this is by sandwich theorem. Okay. Example 5 then, if you're ready. You're not yelling at me to not be ready, so. The limit as x approaches, what's that say, pi over 4? Limit as x approaches pi over 4 of the natural log of tangent x. Well, do you know what the natural log of tangent x looks like?
No.
Do we get to use our calculators?
And then draw a picture.
Well, I want us to think in terms of one of our pieces of information we looked at earlier. We don't know what the natural log of tangent looks like,
No.
but tangent is inside the natural log. Do we maybe know what tangent looks like? I mean, let's go with the idea of you're supposed to have an idea of what tangent looks like. Kind of, dig in deep in your head. So the idea is, Wade, you said what, number 7 from the previous page? The idea is I can take the natural log here, since it is the outside function, and I can pull it out. So this is going to be the natural log of, and now make it the limit as x approaches pi over 4 of tangent x. Now this is a little more doable, because I can think about the limit as x approaches 4 of tangent pi over 4 of tangent x. You can.
What else to do?
Okay. So if we draw a picture. So if we draw a picture, and I don't know, how much do you guys remember about tangent?
It's sine over sine. No, it's sine over cosine. No.
And you go over and it keeps doing the same thing both ways.
Right?
Yeah.
Now, that's the easy part to remember. The harder part to remember is what's going at each piece, right? But you see that it's continuing along.
Yeah.
Do you know something about the tangent at pi over 4?
Oh, the unit circle. Where's pi over 4 in the unit circle?
No.
Or just knowing your chart? The reference chart
That
that
one, no, it's the one on the bottom one.
the quiz my kids just took yesterday.
It's the one.
It's 1.
Okay, tangent of pi over 4 is 1, yes? Well, think about that. That means, okay, it's somewhere, I don't know, say here.
Okay.
Is that limit going to approach 1? This isn't like a removed separate point or anything, right? So if pi over 4 is, say, right here, 1 is right here, it's approaching that point, right? So we could argue that the limit as x approaches pi of 4 of tangent x is 1. Okay, because a limit's going to equal that value as long as there's not like a discontinuity or a hole in the graph or something.
Isn't the natural log of 1 0?
And the natural log of 1 is 0. Done with the problem.
So the answer is 0, or is that no solution?
Answer is 0.
If that exists at 0, or is it?
The limit of the natural log of tangent x as x approaches pi over 4 equals 0. So, okay, I know you guys wanted to graph earlier. If I graph the original natural log of tangent x, right? Is that what it was? Now, I'm just going to do a zoom 6. Okay. My calculator's not doing great. Actually, let me do a zoom 7, because that's Z-trig. That looks a little bit better. Now, where is pi over 4? Well, hard to know. Do you remember how you can, if you hit trace, you can type in an x value. So I can type in pi divided by 4. I can hit equals.
You did trace and then what?
I typed in an x value, and it'll give me the y value.
Do you have to?
So like if I'm on the graph, you could actually do, it's a second calc. It's number 1 if you want to do second calc. But it'll give you an x equals box down at the end. And you can type in, so if I want to know what the y value is when x equals whatever, I type it in. So if I type in pi divided by 4, well, notice it changed pi divided by 4 to a decimal, okay? Negative 9.99 e to the negative 14.
0.
Yeah, they're trying to tell us 0, because that's like scientific notation. They're saying move your decimal 14 places left. Well, that means I'm going to have 0.00000, like 13 zeros, and then the 99. So essentially they're saying that this is 0. Okay. If you look, my cursor even went right there too, and it's showing 0. So there is the proof that what we did makes sense.
The next problems are all pictures.
Okay. So we're going to be drawing some pictures, right? These are just some special limits to be familiar with. The limit as x approaches 0 of 1 over x is undefined. Do you remember what 1 over x looks like?
It's the first and third.
It's our reciprocal function. It's in the first and third quadrants. So it's that hyperbola. That's my sketch. Does that look familiar? Do you agree with the statement then? The limit as x approaches 0 is undefined. Huh?
There's not a point at 0.
It doesn't have to be a point at 0.
They're pointing in different directions.
Yeah. Remember, if a limit is true, it has to approach from both the left and the right. Over here, if I trace from the left and I'm getting closer to 0, where are my y values going? Negative infinity. As I approach 0 from the right and get closer to 0, where are my x values going? Positive infinity. So now I've got one going to negative infinity, one going to positive infinity. Are they going to meet? Are they going the same place? No. So thus my limit is undefined. Okay. The limit as x approaches 0, 1 over x squared. Do you remember what happens if you square that x?
They both point in the same direction.
Yeah. The x squared makes them both go positive. So we've already got the hyperbola in quadrant 1. The one in quadrant 3 becomes positive, and so they're both here. Okay. As x approaches 0 from both sides, x is approaching 0 from both sides, where's my graph going? They're both going up to infinity. So that means my limit does exist as infinity, because they're going the same direction. Okay, so remember, for a limit to exist, they have to be going the same place. What if I put a negative on that graph? Yeah. A negative out front is going to reflect it over the x-axis. So that means my hyperbolas that were in quadrants 1 and 2 are now going to be down here in 3 and 4. The limit as x approaches 0, where are my graphs going as we approach 0 from left and right? Down, and so that's negative infinity.
Are we going to have to memorize? Oh no, is this like the 12 functions thing all over again?
They are helpful to just know what those graphs look like.
After all the homework and stuff, will we just know them and practice, or is it something we need to sit down?
I would say the more you work with them, the more you'll know them. Okay, that's what it comes down to. Just work to become familiar with them as opposed to, okay, let me put you in the calculator. Like, make some effort as you do that to, okay, I had to punch in the calculator this time. This is what it looks like, you know. I'm not going to say it's something that I'm ever going to test you on or anything like that, but it's beneficial. Now, these bottom three, they're helpful to be familiar with. Obviously, you guys are going to tell me you don't know what that graph looks like, right? Whoops. Clear it. There we go. So it is the absolute value of x divided by x. It's almost a straight line, except, yeah, there's a jump in there. So the left side of the straight line is running across that -1. The right side of the straight line is running across that +1. And now, can't really tell it here, but officially, there would be holes on the y-axis because My denominator is x. X cannot equal 0, so I can't have values existing on the y-axis. Okay, the limit as x approaches 0. It says it does not exist. Does that make sense? Because as we approach 0 from the left, what's my limit equal? -1. As we approach 0 from the right, what's my limit equal? +1. Okay. Next example. Notice the graph. Can you draw that graph?
Just talking about
Isn't that the same graph? It's still absolute value of x over x. So you still got the top part and the bottom part. What's the difference in this? What's this question asking? The limit as x approaches 0 from the right. Does that exist? Yeah, as x approaches 0 from the right, we are approaching the y value of 1. And lastly, this is an interesting graph. I don't even know if I can do it justice drawing it. The sine of 1 over x. I'm going to do a zoom 7 for a trig zoom. I feel like it might work better. I don't know.
interesting.
Okay. So you can see the outsides, and then in the middle it just kind of went zzz. Okay. Heart monitor. Good. Now, we are being asked the limit as x approaches 0. I don't know about you guys. I can't tell much about what's going on there at 0. So I'm going to zoom in.
Oh, that looks like my doctor's signature.
So it's a heart monitor. It's a doctor's signature. It did.
Zoom again.
You can zoom again. I'm curious. If I hit trace and I type in 0. Okay, so right there, I did the whole trace thing, and I typed in x equals 0. Notice what my y says. It's blank. Which what that means is there's not, either not a value or not just one value. Zoom in. I forget if we can see this eventually when we zoom in.
It gets worse every time.
I know, and I can't remember.
Do that. Just sorry.
What?
Take your calculator and look at it from right there. If there's like optical illusion things, like see where you do that.
Okay. Somehow okay. This is getting worse every time, and I can't remember how.
Did we graph our to begin with?
Yeah, we did. I don't know. I can't remember.
Try doing the thing. Just see if it works.
What I have shown here is that, I don't know, this one ends down here, and then this one picks up here. That's not a very good graph on my behalf, but the idea is, notice, do you see why it says does not exist?
Yeah.
Because they do not approach the same value from left and right. I really thought, I don't understand why it's getting worse when you, yeah, I don't know.
That was the last one.
No, I don't remember having that problem with the graph in the past, so that's why I'm kind of, did I do something wrong? I don't know. I'll have to work to get the technology to cooperate with me because it's not cooperating, but